All right, here are the answers for some of those tasks that I was asking you to complete in the previous video. So the pyramid of energy that you should produce would look something like this. Now I am going to offer, again, in order to get these values inside of these boxes, this is not a proportional pyramid of energy. So if your producers are approximately this big on your page, what you can kind of do is figure out what would about a tenth of that be. One way you could do that is you could cut it in half. You could cut it in half again. That's going to be about a fourth, and you're looking for about a tenth. So it's going to be a pretty small sliver. Again, about 1/10 of the width. From there, the next group should be 1/10 of that, so it's basically going to be a line. That is what it would look like if you were doing it proportionately. Again, this should be labeled as producers, primary consumers, and secondary consumers. And the values that you should be able to determine would be thus. About 600 kilojoules per meter squared year in the producers, or 6 times 10 squared. Primary consumers then are only going to have 60 kilojoules per meter squared year, and only 6 kilojoules per meter squared year in the top group. From there, you should be able to calculate the energy lost by the plants, or the producers. If you rearrange the equation to solve for R, you'll find that R is equal to the gross production minus the net production. So the gross production for this group was 600. From there, the net production was 500. So if you do the subtraction, you'll find that 100 kilojoules per meter squared were lost by the plants due to cell respiration. Continuing on, calculating the net production of the autotrophs, again, using this equation, if you have the gross production of 43,510 and the amount lost for respiration is 23,930, then the amount that you should get as net production would be 19,580. Don't forget the units, kilojoules per meter squared year. In addition, you should be able to compare the percentage of heat lost. So the amount of heat lost, 23,930, divided by 43,510, the percent of heat lost, it's about 54.5%. It's a significant amount. But if you compare that to the amount in the autotrophs, 14,680, and oh my gosh, 14,140 lost for respiration, 14,140 over 14,680, that's 96.3%. So the autotrophs are losing much less of their energy to heat than the heterotrophs. Why would that be? Well, it turns out that heterotrophs are going to be doing a lot more activity. They're moving, they might have homeostasis of their body temperature. So if they're endotherms, they are maintaining an internal body temperature. That is not a feature of most plants. They are maybe moving, avoiding predators, foraging, hunting, doing predation. And it's also worth noting that there may be a reproductive effort here as well, whether it's searching for mates, competing or fighting for mates, and then of course the tasks of raising young, those are energetic processes as well. So for all those reasons, heterotrophs are going to be in a little bit of a more unique position to burn that energy, use cellular respiration, and lose that energy as heat. And that, ladies and gentlemen, is the unit on energy flow. Thanks for working with me as we do our first unit remotely. Again, reach out if you have any questions. I would love to help. And I'll catch you on here for the next unit.